Hello, everyone, and welcome to my first of hopefully many. I'd like to do a series on this. Welcome to my first video on Squircles. This one is really just going to be an introduction to what actually a Squircle is, and also we're just going to be deriving the formula for the area of one in 2 dimensions. Hopefully, we can get to three and eventually n dimensions, or well, I guess m dimensions, in the future. But yeah. So to begin, what actually is a squircle? You're probably oh, yeah, I was kind of looking at the beta function earlier. Don't worry about that. Anyway, we will be using that if you were curious. So this looks mostly like a square, right? You'll notice that these corners right here are slightly round, and that's basically what a squircle is for high values of n. It's basically a square. But if we were to decrease this n to say, I don't know, let's cap this at 10, to say 2, oh, it's a normal circle. If you make this higher, so for higher and higher values of n, it's basically a square. For lower values, it's more of a circle, and then we're not going to worry about once less than 2, you get weird shapes like that. The point is, basically, when you adjust n, you're adjusting basically how much of a square it is slash how much of a circle it is. And r here is just r, how big it is, basically. So yeah, that's basically what a squircle is. It's not too bad until you get to the integration bit. So say you want to find the area of this squircle here. How would we go about doing that? Well, what we can do is write down the formula for a squircle. So we have x to the n plus y to the n equals r to the n. And what we have here is, let's start equation for a squircle. I'm just going to solve for y here. It's really not too bad, it's just some algebra. So we have r to the n minus x to the n, all to the 1 over n. You can verify that if you want. And this is the function we're going to be integrating, because this is, well, technically this is like only the top half of the squircle, but it really doesn't matter all too much, because the way we're going to set up our bounds are, well, I'll show you now actually. So we're just going to be integrating from 0 to r of r to the n minus x to the n to the 1 over n dx. Now, you might be wondering, why are we just kind of ignoring these absolute values here? The reason for that is, so our bounds are only for the first quadrant, basically meaning this bit right here, where x and y are both positive, so absolute values don't matter there because it's already positive. And if we take this first quadrant, area of that, multiplied by 4, you'll notice we have 4 quadrants. Find the area of 1, find the area of the whole thing. So what we're going to do is find this integral right here, multiply by 4. That's going to be our answer for the area of a squircle. So it's really not that bad so far, but we'll see. Shouldn't be terrible. So, to begin with, actually, I'm going to express this, our integrand, in terms of, I'm going to factor an r out. You'll see why. So it uses the beta function. But this is the same thing as if this is the same thing as this right here. So 1 minus, so r times 1 minus x over r to the n, all to the 1 over n. These things are equivalent. They just are. So what I'm going to do is replace that. So now we have a 4r integral from 0 to r of 1 minus x to the n over r to the n to the 1 over n dx. That's just the function we're integrating now. I'm actually going to do a u sub for u equals x to the n over r to the n. And basically, the whole point of this u sub is to allow us to use the beta function. So you will actually notice that was the Wikipedia page I had up. I was just double checking something. But what we're going to do essentially is use this beta function to put our area of a squircle in terms of factorials. So yeah. So we're going to find du. This is going to be n x to the n minus 1 over r to the n. R is not going to change. Dx, of course. And what I'm going to do now is two things. I'm going to solve for x and also solve for dx, because what we want to do is actually just plug in an expression of u in for that x. That'll allow us to use the beta function again. And to do that, we need to actually solve for x first. So, not too terrible. It's just this. X is just r times u to the 1 over n. Meaning if we plug this in and rearrange, we're going to get dx is going to be equal to r to the n over n times x to the 1 minus n. I'm just going to sub this in real quick. So it's the same thing. Don't forget the du. So r to the n over n times r to the 1 minus n times ru to the 1 minus n over n du. Okay, so we can simplify this even more actually. So the n's here will just cancel by properties of exponents. So we're going to have r over n times u to the 1 over n minus 1 du. That's just our dx. So what I'm going to do here is two things. I'm going to plug this into our integrand and also substitute in u in it. So here we have 4r, but we notice we have an extra r over n, so it's actually going to be an r squared over n times our integral. I'll get to the bounds shortly. And if you remember, we had an x to the n over r to the n right here. Well, that was just our u, right? So we're going to just have 1 minus u to the 1 over n times r u to the 1 over n minus 1 du. Okay, this is our integrand. Now we just need our bounds. So I'm going to scroll up here so we can get u on the screen. If we consider u of 0, just plug it in 0 here. It should be quite evident. We just get 0 back. Nothing terrible. And if we plug in r, it's actually almost nicer. It's just 1, because you have an r to the n divided by r to the n. That's just going to be 1. So our bounds here are just going to be from 0 to 1. And alright, this is where we're going to employ the use of one of my favorite functions, I think, the beta function. This right here is just equivalent to 4r squared over n times beta of 1 over n and 1 over n plus 1. Order of these doesn't matter. It's kind of cool, actually. And what we're going to do is express this beta function in terms of the factorial or the gamma function. And you can go into Wikipedia, as I was doing, or Wolfram Math World, and find multiple identities for this. They come up a bit here and there, but we're just going to be using the identity here, where our beta of, say, x and y, this is equal to gamma of x, gamma of y, over gamma of x plus y. And for reference, gamma right here, so it's just gamma of something like x, this is just equal to x minus 1 factorial. That's all. So, using our new identities, we're going to have 4r squared over n times gamma of 1 over n times gamma of 1 over n plus 1 over gamma of 2 over n plus 1. I can squeeze it in at the bottom. Alright, this is our area of a squircle. It looks kind of terrible, but we can actually make it even nicer if we want, because you will notice that we have a 1 over n here, and we also have a gamma of 1 over n. And we also have the identity from here that x times the gamma of x is just gamma of x plus 1, which is actually just x factorial, but I think I'm going to leave it in terms of the gamma function. Actually, no, I'll put it in factorials. It'll look slightly nicer, I guess. Anyway, that's not the point. So we have a 4r squared times, okay, we have an 1 over n times gamma of 1 over n. That's just what? Gamma of 1 over n plus 1, which is the same thing as this right here. So what we're going to actually get is quite nice. We're going to get a gamma of 1 over n plus 1 squared divided by gamma of 2 over n plus 1. And I'm just going to replace this with factorials. 4r squared times 1 over n factorial squared. The order here does matter, most definitely. And over 2 over n factorial. I'll just put that in parentheses anyway. So yes, this is going to be our area for a squircle. I think in the next video I will definitely plug in some values for n, or at least the next video in the series. So we'll probably try it for like say 1, 2. We'll definitely try it for 1 and 2. Oh, then we get to do the Gaussian. That'd be fun. But yeah, we're definitely gonna do it for 1 and 2, and then taking the limit as n goes to infinity. This should be pretty straightforward anyway, but I'll save that for the next video. This is running kind of long anyway. So yeah, anyway, I hope you all learned something and enjoyed. And if you want to know more about Squircles, actually, you should definitely check out Matt Parker. He has some great stuff on Squircles and Lemniscate. And also Dr. Priam, who has some pretty fun stuff on it as well. So anyway, thank you all for watching, and have a great rest of your day.